I'm Adrian, and I'm the research lead and a note taker.
I'm Michael, and I'm the design and documentary lead.
I'm Amir, I'm the group co-lead and outreach lead.
I'm Tyler, and I'm the group co-lead and portfolio lead, and we're Pave the Future.
As urban populations grow, roads and highways absorb and store massive amounts of solar energy. This solar energy accounts for the urban heat island effect, which is when trapped heat in the ground raises urban area temperatures by up to 15 degrees. According to a study published by the European Union in 2019, roads and traffic account for 30% of all of this urban heat, which leads to higher energy demands for cooling and faster wear and tear on infrastructure. Now, this is a problem because all of this trapped heat in the ground is doing us harm rather than being reused and doing us good.
So we found two previous solutions, Huawei from France and the OHM's road energy system from the Netherlands. Huawei covers roads with thin solar panels that generate electricity while cars drive on top. This idea is innovative since it uses pre-existing road space to produce power. The OHM's road energy system takes a different approach. It uses pipes under the road to collect heat from the sun. The heat can be stored underground and reused to melt snow or warm nearby buildings. While they may seem innovative, they also have potential drawbacks. The pros are that they use existing road space, which generate renewable energy, and they store heat from the sun. The cons are being it's very expensive to install and maintain. The solar panels wear out quickly, and they have a very complex setup. Both systems prove that roads can do more than just carry traffic, but they also show what needs to be improved, and that's the gap that our project aims to fill. Those are some previous solutions that were made in the past. Now let's hear about our newest current solution.
To combat this solution, we came up with 3 sketches. Our first idea was inside concrete runoff heating. The idea was we would use storage drain water and heat that water through the road's heat and turn it into energy through a battery converter. Our second idea was a pressure plate that would generate energy. Cars would roll over the pressure plate, and the pressure plate's downward compression would generate energy through the energy converter. Our third idea was reheatable over the concrete pad liquid heating. So how this would work is this liquid inside of the pad that would go on top of the road would be reheatable, and once it heats up, it would be converted into energy. This idea would be over the road as opposed to our first idea, which would require us ripping up roads. After our decision matrix, discussing with our group, and meeting with our mentor, Wesley Sullivan, we came up with a final sketch. As you can see here, the copper wire is embedded in a rubber layer to protect against cars rolling and damaging it. Below that is a thermoelectric junction module, which takes heat differences and converts it into energy. Underneath that is the cool layer, which contrasts with the heat from the copper wire to generate energy through the thermoelectric module. As you can see here, this is a simplified and more understandable version. The sun heats up the copper wire, which the heat from the copper wire contracts with the cool layer underneath the thermoelectric junction module to output energy. The energy outputs 2 voltages per junction of the thermoelectric module.
However, we had a few project uncertainties for its design. Firstly, we didn't know what to use for our cooling layer. We had multiple options, but none of them seemed feasible for this design. Another concern was the durability of our material. We didn't know how well it would be able to withstand the pressure of multiple vehicles day by day. The last concern was the safety of our material under hazardous weather conditions like rain or snow.
So with these uncertainties in mind, we set up a meeting with our mentor, Casey Mashburn. And in that meeting, he told us that when roads get repaved, they actually take the top 2 inches of the road off. And the layer beneath that is the perfect sweet spot to implement our idea. This helped us solve our uncertainties because it gives us the safety, strength, and durability from the asphalt above, and the insulation and ventilation from the earth below.
As Amir just talked about, when they repave roads, they take 2 inches off. Underneath that base pavement, there are holes that connect to the earth. This removes our need for a cool layer because the earth stays at 58 degrees Fahrenheit. So we can place our thermoelectric junction module right on top of that mid-pavement spot. We can then repave the road. The road's heat and the cool from the earth contrast to generate energy through our thermoelectric junction module.
But how does this fare with organizational safety?
To keep our project safe, we'll follow laws, codes, and regulations, such as CPSC, which makes sure our product is safe for users. OSHA, which keeps it safe in school or work environments, local codes, which control heat limits and installations, and overall will make sure to prevent hazards and make it safe for everyone.
For Phase 3, we plan on turning our 3D model into a working prototype and working out some kinks so this will work in the real world.
Thank you for listening, and we are
Pave the Future.
It's been a while since you've last heard from us. For the past 4 months, the Pave the Future team has been working to combat this problem through hours of research, prototype development, and testing. It definitely hasn't been easy, but we can't wait to show you what we've been able to achieve.
Audio Jungle. Audio Jungle.
Ever since Documentary 1, we've been drilling mentor meetings to help us figure out how we were going to get this great idea into the form of a physical prototype to show at Expo. Both mentors, Casey Mashburn and Wesley Sullivan, were huge helps during this process. Through them, we were able to completely plan out how we wanted to build and present a prototype. They introduced the idea of implementing plexiglass into our build to allow the audience to see the layers to our design. They also informed us about an asphalt alternative called cold patch. This wasn't only cheaper and more efficient than asphalt itself, it also kept a near 1-to-1 ratio of how asphalt reacts to various temperatures. At this point, thanks to the help of our amazing mentors, we were able to narrow down on a final prototype we want to exhibit at Expo.
Once we knew what we wanted to present at Expo, our team flew into testing. We had bought most of our materials before our requested items or even funding came in, which gave us a huge jump start in testing. But that extra time was much needed as our testing results were far from perfect. During our first iteration of testing, we lacked the materials and knowledge we needed to produce results. We used hand warmers on the surface of the modules and ice packs below to create that temperature difference we knew we needed.
However, this difference wasn't enough. We realized that we would never be able to produce energy with the system we currently had. And on top of that, there was no way for us to see if much energy was being generated, if any. This led us to our second iteration of testing.
During our second iteration of testing, we spent the majority of our time doing research on what we could do to either better our results or testing strategies. After successful research and extra knowledge gained, we bought a heat gun, voltage meter, heat sinks, and extra thermoelectric modules. We used the heat gun on the surface of the modules rather than the hand warmers to better simulate the amount of heat we would be absorbing from the asphalt. However, this time we added the new addition of heat sinks beneath the modules to help us get a more impactful temperature difference. We then used an ice pack in the same relative spot beneath the module and heat sink.
Originally, we've shown you guys an often recurring 3D model of our design work. We take 2 inches off the top of the road and place our modules beneath the removed layer. When roads are repaved, the cooling layer comes naturally through holes placed in the ground for natural ventilation. However, as we all know, this quickly made 3D model wasn't going to be enough for the Expo. Although it was a good starting point, we knew we needed to take it to the next step.
Obviously, we wanted something visual to set on the table for our senior expo, just to show off the design we've been working on. Our first idea was to have plexiglass on all sides of the box, but we realized this wasn't strong enough to withhold the materials we were going to put inside of it. So we shifted to something with wood on each side, with one side having plexiglass, so you can still see inside and show off the design we've been working on. The main positives of our in-house expo was that it was the first time presenting in the expo style to people that weren't our classmates. It gave us great insight to the kind of questions and comments we may receive from our audience, as well as just gave us a good base to refining our presentation skills for our final expo.
After our Shark Tank presentation, we had a Q&A which we used to look at our problem and solution in different ways. There were no real cons, except we used what we didn't know. We researched it to better improve our solution.
We can't thank you enough for your support as we near the completion of this major milestone we've set out to achieve. We hope you'll join us to see all the hard work put together at the Early Colleges Expo on April 29th.